Hi everyone, this is Hal Tasaki. In this short video, I like to discuss the essence of my recent paper, which is actually my favorite paper, on the macroscopic irreversibility in quantum systems. Okay, so here's the abstract. So we shall prove the presence of macroscopic irreversible behavior, which is ballistic diffusion, in a free fermion chain, which is initially in a non-random state. This is important, and evolving under deterministic quantum mechanical unitary time evolution. And I will explain why this is important. And the proof is actually short, but it is based on an accumulation of ideas and methods like ETH developed over the decades to understand thermalization in isolated macroscopic quantum systems. And we also make use of a new result specific to the free fermion chain. Okay. Anyway, let me start with introduction and motivation. It is well known that a physical system governed by a deterministic reversible time evolution law, such as Newton's equation or the Schrödinger equation, may exhibit irreversible behavior. For example, although we do not observe collapsing building often, but we certainly know that this process is possible. But we never see this reverse motion, and we know that it is impossible. So this is a typical irreversibility. And I want to stress that for irreversibility, it is essential that the system has a large degree of freedom. And if you have many, many particles, then even an ideal gas may exhibit irreversible behavior. Here's a simple but useful example in a classical ideal gas. Consider a system of n free classical particles on a finite interval with periodic boundary condition and assume that the number of particles is huge. Okay? And then I assume that initially all the particles are at the origin, and the velocity of the jth particle is drawn randomly, independently, and uniformly from this interval. Okay. Now, since this is just a free particle, the position of the jth particle at time t is exactly given by this, right? And then if t is large enough, then you observe that these positions are almost uniformly distributed in the interval, this whole interval. So we started from this concentrated configuration, localized configuration, and we ended up with this almost uniform configuration. So we have seen an irreversible expansion or ballistic diffusion. Okay, and here it is essential that these initial velocities are chosen randomly. Otherwise, if you choose this Vj according to some deterministic rule, then you don't observe this uniform distribution. Okay, and this observation leads to a very interesting comparison between classical irreversibility and quantum irreversibility. In classical systems like the ideal gas we have seen, macroscopic irreversibility can be proved, but as a probabilistic statement, which is valid for the majority of random initial conditions. Okay, and this is because there are always exceptional initial conditions that does not lead to irreversibility. Okay, but in quantum systems, it has been believed that macroscopic irreversibility can be proved without introducing randomness, without introducing probability, either in the Hamiltonian or in the initial state. Okay, I think everybody believed in this statement, but here we provide a completely rigorous example, and I think for the first time. That's why I believe this paper is interesting, although we can only treat a free fermion chain. Okay, now I will explain you what we have done. So this is our model. So we consider a system of n non-interacting fermions on a finite chain with L sites. And I assume that L is a large prime number. I know this is weird, but this is needed for this lemma. And I assume n is a large positive integer, very, very large positive integer, and we fix these L and n. And this is our Hamiltonian. This is a very standard free fermion Hamiltonian with uniform nearest neighbor hopping, except for this phase factor e to the I theta. And we need this for this lemma. What is this lemma? Well, this lemma says that all energy eigenvalues of this Hamiltonian H are non-degenerate. I'm talking about many body energy eigenvalues are non-degenerate except for a finite number of theta. In particular, if theta is non-zero and satisfies this inequality, if it is sufficiently small, then all the energy eigenvalues are non-degenerate. Okay, and this statement was proved by using some number theoretic theorems from mathematics back in my old papers, and the strongest version was proved by Naoto Shiraishi and myself in our recent paper. Okay, from now on, we choose such theta. Such theta that this lemma guarantees that there are no degeneracy. Okay, so, well, it is enough to choose theta like this. Good. Then this is our main theorem. So let S be an arbitrary subset. It need not be connected of this chain. And I denote by this the number of sites in S. And NS denotes the number of particles in S. This is quantum mechanical operator. And we focus on this ratio, NS over N. Okay. And then if particles are distributed uniformly, then this operator takes this value, mu, which is number of sites in S divided by the total number of sites. Okay. So this is the equilibrium. Mu is the equilibrium value of this operator, NS over N. Finally, we fix an arbitrary, very small precision delta for measuring this operator. Okay. And then here's our theorem. You take any initial state phi 0. It can be anything. And also take sufficiently large positive t. Then there exists a set A, which is a subset of this interval. And actually, A stands for atypical, which first of all satisfies this inequality. What is this? First of all, this L of A denotes the total length of this A, set A, or you can call this the Lebesgue measure of A. And this total length, the Lebesgue measure divided by t, is upper bounded by this. But what is this? Well, here you have exponential and you have everything, several things which is of order 1, mu and delta. These are order 1 quantity. Delta may be small, but they are order 1. And here you have n. This is a huge macroscopic quantity. So it means that this exponential to the minus something huge is, of course, very, very small, negligibly small. Okay, this is very small. And then I can prove that for any t within this interval, but not on this A, which means that it is not in this atypical subset. So this means that t is typical. Okay? So this is the picture. This is the interval. And this is atypical subset is here. And I have to stress this. And this inequality says that LA over T is negligibly small. This means that this atypical subset is a real minority. Most of this interval belongs to this green region, and this purple region is very, very minor. Okay. And so if you take any T from this green region, if you take any typical t, then this inequality is valid. What does this mean? Well, again, the right-hand side, these are the same quantity. So the right-hand side is, again, negligibly small. It's essentially 0. And here on the left-hand side, you have this expectation value. And what is this phi t? Phi t is the state at time t. And we only consider isolated quantum system. And so the time evolution is written by this unitary time evolution, unitary operator. Okay, and so this is the expectation value with respect to this phi t, and here is the projection operator onto the event that this ns over n, the difference between ns over n and its equilibrium value is larger than delta, our precision. Okay, so this is the event that if you measure this, then you get a result different than the equilibrium value within this precision. And this inequality says that the chance of such event is upper bounded by this. So such an event essentially does not happen. So this means that whenever if you measure this, you get this. That is the rough statement. So, okay, so this is a formal statement, formal perfectly rigorous statement. So let me rephrase this. I already did, but let me rephrase this in a less formal manner. Okay, so the theorem said that for any phi 0, for any initial state, for sufficiently large and typical time t, that means all t from this green region, the measurement result of ns over n in this time-evolved state phi t almost certainly equals the equilibrium value. Okay, so this is the main statement. And what does this say? For example, this says something like this. So let phi 0 be any initial state where all particles are in S. So I didn't write, but for example, S is something like this. And so in this case, this is a bad right notation, but you have this in this initial state. Everybody was in S. Then our theorem says that our theorem applies to any phi 0. So our theorem says that for phi t for sufficiently large and typical t, this ns over n is basically mu. So it's like this, and it means that we have almost uniform distribution. So we have this transition from this concentrated configuration to almost uniform configuration. And everything is just, the time evolution is simply governed by this unitary time evolution. Okay, so we can say that time arrow has emerged from the unitary time evolution in an isolated macroscopic quantum system. And this is important. We don't have to introduce randomness in the initial state or the Hamilton. And I also stress that it is essential that we focused on this macroscopic observable. Okay. Here is one remark. And so this is what we have already seen. And I think you know what I'm talking about. I'm going to talk about. So now let me choose a new initial state psi 0 like this. T0, T naught is a sufficient large and typical T. So for example, this T. Okay. And this is phi T naught, and this star denotes a complex conjugate of the wave function. And so these are, and here in this psi naught, we have almost uniform particle distribution. And then I consider this psi t naught, time evolved state. Okay, this is initial state, and this t naught is a large number. So this is a state after a long, long time. And of course, this is a definition. But from the time reversal symmetry of the Schrödinger equation, you'll find that this is exactly equal to phi 0 star. And so it's the same as this one. Then the particle, of course, complex conjugation doesn't change the particle distribution. So you get this. Well, so you started from this uniform particle distribution, and after quite a long time, you ended up with this concentrated configuration. So is this a paradox? Well, of course, there's nothing paradox here. Everything is mathematically rigorous. Well, so let's recall that what our main theorem says. Our main theorem said that for sufficiently large and typical t, it holds that in psi t, this ns over n is almost equal to mu. Ooh. But here, we have to know that this typical t is chosen for this initial state psi 0. Okay? If you fix your initial state psi 0, then this green and purple region will be determined. So the set of typical t is different for phi 0 and psi 0. So this paradox means that actually this t0 was not typical with respect to psi 0. Okay, and for typical t, you don't observe this. So since this is not t0 is not typical, this means that usually if you do not know t0 t naught in advance, then you cannot. It is very hard for you to observe this kind of transition. And usually you just start from uniform distribution and you simply end up with uniform distribution again, nothing. But if you happen to know this t naught exactly, it's a kind of cheat, then you can observe this. Okay, so that's a resolution of this paradox. So anyway, the main theorem is always true. For any initial state, you observe uniform particle distribution for typical sufficiently large and typical t. Okay, so these are the main results, and let me talk about ingredients of the proof, but this is, I only have 2 slides, so it's just quick. And the most essential technical result in this present work is something called the strong ETH bound. Okay, this is our Hamiltonian, and if you know something about free fermions, then you easily find that the energy eigenstates are exactly written in this way with the creation operator corresponding to the wave number k. And this both phase k is a collection of wave numbers. Oh, of course, you don't have to care if you don't know this. Then our basic lemma is that for every energy eigenstate psi k, we have this inequality. And this projection operator is the same as the one we treated, so this looks familiar. But in this case, we are taking expectation value with respect to an energy eigenstate and saying that this is, again, very, very small. So this, in words, this means that ns over n almost certainly equals mu in every energy eigenstate. And I would say that this is a version of strong ETH, strong energy eigenstate thermalization hypothesis. What does it mean? If somebody states a property of quantum system for every energy eigenstate, then this statement is called strong ETH. And this is precisely the strong ETH in the form of large deviation that was formulated by myself several years ago. Okay, and actually, this is the first non-trivial example of the property that I stated here. Okay, so this is one important. The proof is actually not very difficult, but this is the main, the essential technical result in our paper, new paper. And then here comes ergodicity version of main theorem, and it's very easy to prove. So let me show you how to prove it. So let's take any initial state. It can be anything, and you can always expand it using energy eigenstates. Okay. Then the time-evolved state, this is the miracle of quantum mechanics. The time-evolved state can be compactly written like this, as you learned in quantum mechanical class, or as you, actually, I taught this rather recently. So this is time-evolved state. Then if you have this, you can compactly write down the expectation value of any operator, any projection operator like this. Okay, so here you have double sum and this oscillating factor and this, matrix element. Now I want to consider the long time average of this this t-dependent expectation value. Okay, so this is you simply integrate from 0 to t and let make t divide by t and let t go to infinity. Okay, now you recall this lemma, which says that all energy eigenvalues are non-degenerate. Suppose that k and k prime are not equal, then this lemma says that ek minus ek prime is non-zero. So this term, this exponential term oscillates, but then oscillating term vanishes because of this long time average. So now this means that the contribution only comes from k, where k and k prime are the same. Okay, so this means that this double sum changes into a single sum. This becomes this alpha k absolute value square, and this vanishes, and this becomes this diagonal matrix element. Okay, now, so this is a very simple formula, and now I recall this important lemma, strong ETH. And this says that this term is bounded uniformly in k, like this. So if you just plug in this projection operator here, you find from this and this that the long time average of this temporal expectation value is upper bounded by this. Okay, so the main theorem that I discussed before was a statement about this time-dependent expectation value for sufficiently long and typical t. But if once you have this time average version, ergodicity version, then it is rather easy to prove this the first version of our main theorem. So that is something you can read in our paper. Okay, so that's basically all. So I want to go to the summary and remaining issues. So we proved the essence of the presence of macroscopic irreversible behavior in a free fermion chain, initially in a non-random state. As I said, this is important, and evolving under quantum mechanical unitary time evolution. We didn't have to use probability for initial state or the Hamiltonian. And the proof is based on this strong ETH things, okay, which has been developed over decades to understand thermalization problems. Okay, and also we used results about the absence of degeneracy and strong ETH that can be proved only for free Fermion chain. Okay, And there are many, many remaining issues. Extension to other observables. Probably this is possible. We have to discuss actually time scale for equilibration. I don't know. Probably that is possible for free fermion system, but I don't know how to do that yet. And of course, we are not satisfied with a free fermion. We want to treat non-integrable systems, but this looks formidably difficult for the moment. But anyway, we have to keep on thinking. Okay, so thank you very much for watching. Goodbye.